yeah, this is a merge of two works. The first is Oblivious Transfers in MiniQCrypt by Alex, Huijia, Fang, and Vinod. And then there's one-way functions imply secure computation in a quantum world, which is joint work with Andrea, Dakshita, and Fermi. Okay, so this talk is about secure computation. So I'll begin by defining what that is. So here we consider a set of parties. They each have some private input, xi, and their goal is to compute some circuit over all these private inputs such that they all learn the result of this circuit. Okay, and they're just going to do this by communicating back and forth with each other. And security states that if any subset of these parties are corrupted by an adversary who's like arbitrarily, maliciously controlling their actions throughout this protocol, then it's still the case that the adversary can't learn anything about the honest party inputs, in this case, x1 and x4, other than what it would anyways learn from the output of this circuit. Okay, so this primitive of multi-party computation, or MPC, is extremely versatile. It's has a long history of study. Just to have one example in mind, you can imagine a set of hospitals that each have have their own sensitive patient data, and they maybe want to pool all their data and compute some like statistical analyses on the combined data. So secure MPC would offer a solution where they don't have to compromise the privacy of their patient data. Okay. Right. So like I said, this has quite a long history of study, mostly in the classical cryptography world. And at the center of this study of MPC lies this primitive called Oblivious transfer. Okay, and this is a very special case of MPC. It's actually just a two-party functionality. Okay, so here we consider a sender party that has as input two strings, S0 and S1. We have a receiver party with input bit B. They interact, and at the end of this interaction, the receiver should output S sub B. Okay. And the receiver shouldn't learn anything about S1 minus B, and likewise, the sender should not learn anything about the bit B. So this is like a very simple two-party functionality. And what's nice about this, and it's been known for a few decades now, that actually, if you can construct a protocol for this very simple functionality of oblivious transfer, then you can construct a protocol for MPC for any arbitrary functionality with any arbitrary number of parties. Okay, so if you want to construct general purpose MPC, it actually suffices just to construct a protocol for oblivious transfer. Okay, and over the years there have been many constructions of OT from various assumptions. For example, learning with errors assumption, decisional Diffie-Hellman assumption, various other assumptions. Which is great. We know MPC from all of these assumptions, but kind of one of the overarching goals of cryptography is to base your cryptographic primitives or your constructions on as weak of assumptions as possible, right? And kind of the weakest assumption that cryptographers know that cryptographers know to be useful for building cryptography is called one-way functions. Yeah. And a one-way function is just a very generic assumption. And unfortunately, since, again, like 3 decades ago, Impaglaser and Rudich showed that you actually cannot construct oblivious transfer based solely on the hardness of one-way functions if your construction uses those one-way functions in a black box way. So like doesn't use the code, the implementation of the one-way function, just kind of treats the one-way function as a black box. Okay, so this gives like basically a black box separation between oblivious transfer and one-way functions. And moreover, like even to this day, I don't think there are really any even like plausible approaches for constructing OT even from non-black box use of one-way functions. So at the very least, it seems like quite a difficult problem to get any construction at all of OT from one-way functions. And so this is kind of the current state today. Essentially, for MPC, we know how to build MPC from various kind of public key style assumptions, like learning with errors and Diffie-Hellman. We do not know how to build and have no really approaches for building it from one-way functions. Okay, so this is the situation in the classical world. MPC has also been studied in a quantum world, and by that I mean where parties have quantum computers, adversaries of quantum computers. Parties can communicate quantumly. You can even consider parties competing quantum functionalities over quantum inputs. And it still holds, even that classical oblivious transfer implies a multi-party computation. And it even implies multi-party quantum computation, as shown by these works of DNS and DGJMS. Okay. But what's also exciting about OT in a quantum world is this template that was first kind of described in the 80s for building oblivious transfer from something called bit commitment, which I'll describe later. But this is a template that kind of doesn't exist in the classical setting and kind of crucially relies on the use of quantum communication. Okay. And so these original proposals didn't necessarily come along with security proofs, but later it was shown, like DFLSS, this work showed how to instantiate this template from the learning with errors assumption. Although this is also known classically. Okay, so not necessarily getting a separation between classical and quantum yet. Another work around the same time showed that if you instantiate this template with one-way functions, you can actually obtain some form of, I'm calling like weak OT, but it's like an indistinguishability-based notion of oblivious transfer that is unfortunately, this definition is not known to imply MPC. Okay, so until our work, this was kind of the state of MPC in the quantum world. Okay. And I mean, to recap what I just said, this is kind of the situation in the classical world. This is what's going on in the quantum world. It's unclear whether one-way functions imply oblivious transfer. And so this is where our two works come in. We kind of fill in this arrow. We show that indeed, like simulation-based OT can be based solely on the existence of one-way functions, quantum hard one-way functions, since we're in a quantum world, and which establishes that general purpose MPC can also be built from one-way functions. Okay. And cryptographers like to sometimes call the world, or any primitive that can be built from one-way functions kind of resides in this world called MiniQCrypt. And so you could kind of define the same world, but in the quantum setting, you could call it MiniQCrypt. And what our works are showing is that actually MPC, while outside of MiniQCrypt, or at least thought to be outside of MiniQCrypt in the classical world, is actually inside this world of MiniQCrypt. It's a primitive that can be built just from one-way functions. Okay. So yeah, before I'm going to explain kind of this template and how we instantiate it, but first let's just refresh on what oblivious transfer is. So it's this two-party functionality, and let's get a sense of the kind of security that we're going for. Okay, so let's say that we want to protect against a malicious receiver interacting in this protocol, and remember, so this malicious receiver can interact however it wants. It outputs kind of a final state. And we want to ensure that this receiver only learns one of these two sender strings. So how to argue that is to say that there exists a simulator that can simulate the view of this receiver only given one of these two strings, which is formalized by saying that the simulator doesn't have access to the actual sender. It has access to this oracle that it can query once on a bit B and receive one of these two strings. The simulator, just given this information, should be able to simulate the entire view and output of a malicious receiver. Okay. And so note that in order to do this, actually what a simulator has to do is to take the description of R and somehow, like by maybe interacting with it or whatever, it has to somehow extract the implicit choice bit B that R is using in this protocol. Okay. So crucially, in order to get this simulation style notion of security, what we need to be able to do is extract inputs from malicious parties. And so this is going to be something to keep in mind as we go through the OT protocol. Okay. Yeah, so now I can I can describe how this template for OT from bit commitment kind of works. So if you've seen like quantum key exchange, you'll notice a few similarities, and the protocol starts much the same way, where we have the sender basically sample a bunch of BB84 states, so a bunch of bases and bits, and send those states across to the receiver. Okay. So at this point, the receiver has no idea what is encoded in these states, and it's just going to sample its own random bases phi prime. Okay. And so it'll be correct about half the time, right? So these green positions, it guessed the right basis. The red ones, it guessed the wrong basis, and it will just measure the qubits in the bases that it sampled. And so, of course, the positions that the measurement outcomes corresponding to its correct guesses will coincide with the sender's bits, and then the red ones will just be kind of random and uncorrelated. Okay. So let's say the receiver receives the qubits that measures. Then the sender will send over the set of bases it used. So it says, here are the bases I used. And this gives the receiver the information like, oh, okay, I guessed right on this particular subset. I guessed wrong on this other subset. And so the receiver can like partition the indices into these two sets, right? And it will assign, so its choice bit is B. And it will assign the set of indices where it guessed correctly to be I sub B, and the set of indices that it guessed incorrectly to be I sub 1 minus B, and it will just send these two sets over to the sender. Right, so these two sets basically tell the sender how to partition its string X into these two parts. And what they guarantee is that basically the receiver knows one of these two strings X and kind of has no information or very little information about the other string. And the one that it knows is XB. So the sender will use some sort of encryption. For this talk, doesn't really matter what it is, to kind of encrypt its string S0 under X0 and encrypt the string S1 under X1. Which allows, since the receiver knows XB, that allows the receiver to recover the string SB, but not the string S1 minus B, right? So this is kind of the initial basic idea of how quantum communication might help with OT, by kind of essentially what it's doing is you're setting up an eraser channel using quantum communication. Okay. But there's a fairly simple attack. If the receiver can simply just refuse to measure here and just wait for the sender to send over the bases, right? In this case, the receiver can just measure in all the correct bases and learn the entire string X if it just waited for this. Okay, and in that case, it can clearly just decrypt both these strings, which is a security violation. Okay. So to fix this attack, these initial works, they use something called bit commitment, which briefly is like the following primitive. It's basically a cryptographic version of a locked box. So we have a committer that wants to commit to a bit B to a receiver. It essentially sends a locked box filled with B. And the hiding property states that the receiver shouldn't learn anything about B just from inspecting this box. And then later, we would like to allow the committer to reveal what is inside the box by sending over a key. Okay. And this key allows the receiver to open up the box and learn what B was. And this binding property is saying that C can only open the box to B. Once C has sent this box, the only thing it can only send a key that will cause the receiver to open and learn the bit B, and not say 1 minus B, right? So these are the two basic properties that you usually assume from a bit commitment: this hiding and binding. So you can use bit commitment basically to block this receiver's attack as follows. So what we're going to do is, instead of just trusting that the receiver measures these properly, we're going to have the receiver measure and then commit to all its measurement results and send them all over to the sender. And the sender issues a random challenge, which is just, can you please open up a subset of these commitments that you sent? the receiver will oblige and open, in this case, the second and the fourth commitment. And so now what the sender can do is just check the openings and say, okay, well, for all the positions that are green, meaning for all the positions that the receiver actually guessed the basis correctly, well, if they measured honestly, then they should have received exactly the bit that I encoded, right? And so that's what the sender will check. It'll open the subset, it'll check all the green positions and check that they all match X. And if they all do, the sender can be reasonably convinced that the receiver actually measured properly. And so then they can continue with the protocol. Although this used up basically a couple of these qubits essentially, but they can continue the protocol on the remaining subset of 4 qubits. Okay. So receiver will split them up and the protocol continues as before. Okay, and so yeah, we just kind of inserted this this sub protocol that we can call measurement check sub protocol. And this is kind of the template that was introduced in these earlier works for how you might build oblivious transfer using quantum communication and a bit commitment. Okay. So yeah, like I said, these original works didn't necessarily come with security proofs. However, this work in 2009, DFLSS, what they showed is that if you want to, you can obtain, you can show that this OT satisfies simulation security as long as the commitment scheme that you use satisfies certain special properties. Okay, and these properties are called extractability and equivocality. And I'll get to describing what exactly these mean, but we'll see, and what they showed is that if your commitment is extractable, then you can actually obtain security against a malicious receiver, and if your commitment is equivocal, you can obtain security against a malicious sender. So, okay, to see what's going on there, let's say we want to show security against malicious receiver. What I described before about simulation security requires that we actually are able to extract the choice bit B from our receiver, right? So basically, we want to say that there exists a simulator that can interact with R and extract this bit B. And so what we're going to do is assume that somehow, like this commitment scheme, magically has the property that a simulator interacting with R can actually extract directly from these commitments. So let's say that we can just take these commitments and extract directly the bases phi prime and the measurement results x prime. In that case, when the receiver later sends over its 2 sets, I0, I1, it's fairly easy to see that you can just compare. You can compare phi and phi prime to see where the receiver actually guessed correctly, and from that deduce which of these sets correspond to its choice bit B. Okay, and so you can directly infer what is B from these 2 sets. Okay, so this is explaining that yeah, if you can extract from your commitment, then you can extract from an adversarial receiver in this protocol, which is quite useful for showing the simulation security. So on the other side, we also need to show security against a malicious sender, and it's kind of the same deal. We need to identify a simulator that can extract the sender's input, and for this we use equivocal commitments. And so recall that a cheating receiver, their strategy was just to delay measurement and wait for these bases to come in until they measured, and at that point they can kind of learn both sender strings, right? So we can actually delay this measurement as long as we can equivocate these commitments. And by that I mean, if while simulating S, we can somehow send S some kind of dummy commitments that kind of don't commit to anything in like an indistinguishable manner, then like when the sender sends its test set 2, 4, at that point we can only measure those 2 particular qubits, and then open these equivocal commitments to anything of our choice, which will just be the measurement results. Okay, so if you could do that, then note that at this point the simulator has not yet measured the other 4 qubit positions, and so they can just wait for the sender to send the bases and then measure those. And then at that point, everything is green. They can just learn all of the rest of the bits of X and then decrypt and learn both of these sender strings. So this is kind of the simulation strategy for extracting a sender's input based on equivocating these commitments. Okay. So this is, this is kind of where prior work ends, and this is kind of what was known before our work. And so naturally, our goal then is to say, well, if we can show, our goal is to show that you can construct quantum secure, extractable, and equivocal commitments from just quantum hard one-way functions. And that would imply then simulation secure OT and then MPC just from one-way functions. And so the two works that are being talked about today actually approach this problem in fairly different ways. And I will, so the GLSV part of it, I will let Alex talk about. For our part, we basically have two steps, I guess. So one is this this black box equivocality compiler that we show, and this is what we show is how to take any commitment scheme. It doesn't matter how it's implemented or how much communication is happening or whatever. We show how to, in a black box way, turn it into an equivocal commitment. Okay. And our second contribution is to say, well, if we have an equivocal commitment and we have quantum communication at our disposal, then we can we can construct an extractable commitment. So given these two tools, our final construction goes as follows. So if you we just start with a commitment from one-way functions. I'm saying a vanilla commitment, it just satisfies just the standard hiding and binding properties, and this we know from Nauer's commitment. So we first apply our equivocality compiler to get an equivocal commitment, and then we plug that into our second step, right, to obtain an extractable commitment that uses quantum communication. But the second step actually, at this point, it's actually no longer equivocal. It just applies an extractable commitment. That's okay. We can just apply our compiler once more and obtain an extractable and equivocal commitment. Okay. So that's the outline of how we obtain the final result from one-way functions. And I can now say a few words about each of these steps. So actually, starting with the second one, it's a little simpler to see based on what I've already described. So recall the slide that I just had up a couple of slides ago, which is where I was arguing that if you had an equivocal commitment, then you could extract S0 and S1 from a malicious sender in the OT protocol. So it's basically showing that equivocation implies extraction in the context of OT. We can simply repurpose the same kind of argument to show that equivocation implies extraction in the setting of commitments. So if we replace the sender and receiver of OT with just say an extractable, or say a committer who's attempting to commit to a bit B to a receiver, and in this last step, rather than kind of encrypting both strings S0 and 1, it just like takes all of the bits of X and uses them to encrypt their bit B. What we can show is that the same exact kind of extraction strategy will work. So if you can equivocate your commitment and delay measurement, then you can extract from this commitment. Okay, you can extract the bit B at the end. Okay. Great. So that's that's one of our two steps, and it really just remains to show this black box equivocality compiler as how can we construct an equivocal commitment while making only black box use of any arbitrary commitment scheme. And so that proceeds as follows. So our committer will just actually sample 2 random bits and then send over 4 commitments to the receiver using like the underlying whatever commitment scheme we want to use. And these 4 commitments are supposed to come in 2 pairs, where the committer commits to U0 twice, and then U1 twice. And so at least that's what an honest committer will do. A receiver will want to check that this committer is being honest by issuing a random challenge and basically saying, hey, either open up your top row or your bottom row so I can be sure that you're actually committing to the same bit. And so let's say for the purpose of this slide that the receiver challenged with 0. What will happen is that the committer will open up these top two commitments, trying to convince the receiver that, hey, look, I was being honest and committing to the same value. And then it will actually commit to B by using U1, because at this point, U1 is still hidden from the receiver, right? So committer will open these and then mask B with the value U1. Okay. So that concludes kind of the commit phase. And then to open, committer can simply open either one of these two commitments, U1 or U1, since they should be the same thing anyways. The committer will just send one opening. The receiver will learn what is U1 and be able to unmask to learn the bit B. Okay. So, and I will say this is a this is kind of a simplified version of the actual commitment scheme. In particular, we have to kind of repeat this sub-protocol like many times sequentially in order to get full-fledged binding property. But to quickly give intuition for why is this equivocal, so what we want to do is we want to kind of simulate a receiver and allow and kind of like cheat in our commitment while we're simulating this receiver, such that the commitment is equivocal. So what we can do is basically be honest in one of these two rows and be dishonest in the other one, commit to different values in the other row. And now, since we're simulating receiver, we have, like, say, the ability to rewind the receiver. And we just want to rewind them until they issue the challenge that we like, which in this case would be challenge 0, because we can actually show that we're being honest in the first row. So we rewind until c equals 0, then open up the first row, and then just send some random value for the actual commitment. It doesn't matter. The point is that later, when we want to open, since these are commitments to different bits, like either opening this one or opening the other one will cause the receiver to obtain one bit or the other. And so we can kind of retroactively at this point decide, like, what is the bit that we actually wanted to have been committed to. Okay, and that's where this equivocation is coming from. And yeah, so by the way, this rewinding, while quite a common technique in the classical setting, certainly runs into issues in some cases in the quantum setting, but this is a situation where we can apply a Watch's rewinding lemma. Okay. So yeah, that's the technical part of the talk I wanted to give. And just so before turning it over to Alex, I wanted to just mention a couple nice features of our construction and our approach more generally. So what we end up showing, essentially because our equivocality compiler is black box, what we end up showing is how to construct OT that only uses the underlying one-way function in a black box way. Okay, and so this is, I guess this is interesting for a couple of reasons. One is that in the classical setting, like I mentioned at the beginning of the talk, we actually know that it's impossible to construct OT from black box use of one-way functions. So this is giving an example of something that we know to be impossible in the classical setting, but achievable in the quantum setting if you allow quantum communication. I guess, and another reason it's nice is that, so essentially we're making black box use of an underlying commitment scheme that just satisfies standard hiding and binding. And so if at a later point, someone comes up with a commitment scheme that, maybe uses quantum communication and is based on some assumption that might be like maybe weaker or incomparable to one-way functions, then you can immediately plug that into our protocol and show that OT and more generally MPC follows from that same assumption. Okay. And then finally, yeah, another thing to note is that one side of our security proof is statistical or unconditional in the sense that we don't have to use any computational assumptions to show security against a malicious receiver. We only use the one-way functions to show security against a malicious sender. And so, yeah, so that's all I wanted to say for my part, and I will turn it over to Alex.
Okay, so maybe a few questions in between that might refer to your slides. And of course, if there's more questions, then you can always ask them in the roundtables. So there was a question by Zvika Brakeski on how do you generate the CRS, the common random string of the Naur scheme?
Oh no! Oh, we don't use we don't. So you can instantiate that just with 2 messages rather than using a CRS. Okay, so receiver just sends first message and sender responds.
Okay, and then another question again by speaker was that what happens in the semi-honest or specious case? Is this easy to do in the specific setting, the MiniQCrypt?
Oh, getting like specious? No, so it wasn't known before this work, like saying that like one-way functions imply a specious OT. I don't believe that was known. And yeah, so I haven't really thought about if there's any sort of simpler construction. The point is that like specious security doesn't, it's kind of stronger than maybe classical semi-honest security in the sense that it doesn't prevent the receiver from doing that measurement, or it doesn't prevent the receiver from delaying the measurement. So you still have to handle that even in the specious security setting.
Okay, great. Thank you very much for this talk. And then maybe we move on to Alex's talk. So Alex is a researcher at CNRS and LibSys. So the stage is yours.
So thanks, James, for the great first part of the talk. And now I'll present my work with Huijia, Fang, and Vinod, where it showed this second result that showed how to do secure multi-party computation in MiniQCrypt. And as in the previous result, the goal is to start from one-way functions in quantum and build an extractable and equivocal commitment. And then from previous result as a BCS protocol and later the security proof, we can build LT and multi-party computation and so on. But then the route that we use in order to build extractable commitments from these assumptions is fairly different. So first, we also provide equivocal commitments, but our proof is very different from them. So we just do a classical zero-knowledge proof in order to achieve equivocal commitments. And from these equivocal commitments, what we can easily see is that using some variants of the of previous results, we can show that we have some sort of OT where in particular OT where the simulators can run in exponential time instead of polynomial time as desired in order to achieve applications from OT. Then from OT, we show how to build unbounded simulator verifiable conditional disclosure of secrets, and I'll describe what this primitive is later. But just to finish, from this verifiable CDS, we can then show that we can achieve an extractable commitment. And for the rest of this talk, I'll explain or give a sketch of the proof of each one of these steps in order to achieve extractable commitments. So in order to give the first step, I'd like just to recall the definition of zero knowledge. And here we're in particular interested in zero knowledge for relations. So we have a relation that's just the Cartesian product of 2 sets. And we consider a protocol where I have 2 players, the verifier and the prover. And these 2 players, they are giving some input that belongs to this first set X. Then in this protocol, the verifier and the prover, they exchange messages back and forth. And the verifier then decides to accept or reject this input X. There are 3 properties that we want from this protocol to call it a zero knowledge proof. So first, we want that if P knows some W such that X and W belongs to the relation, then V should accept with high probability. Secondly, we want that if there exists no W such that X and W belongs to the relation, then V rejects with high probability. And third, that's known as the zero knowledge protocol. We want that the verifier, even if she's malicious and try to deviate from the protocol, she does not learn any W such that X and W belong to R. Okay, and of course, the issue here, how can we define that v tilde didn't learn anything from W? And we do this by assuming that this arbitrary malicious verifier interact, even in this case, could be even quantum, interact with this prover and output some arbitrary quantum state rho. And what we want in order to show zero knowledge is that you have a simulator that might depend on this malicious verifier, and it also outputs some quantum state sigma. But here it's important to notice that the simulator does not interact with the prover. So the simulator is just a polynomial-time quantum algorithm. And in order to say that this protocol is zero knowledge, our goal is to show that the output of the simulator is indistinguishable from the output of the verifier that interacts with the prover. So in particular, what we want to show is that all polynomial-time quantum algorithms behaves morally the same when they're given as an input a rho or sigma. And in particular, we are interested in NP relations. So we're interested in relations where there exists an algorithm V such that V on input X and W outputs 1 if and only if X and W belongs to this relation. And we had that Watchers proved in 2009 that if post-quantum 1A functions exist, then we have post-quantum zero-knowledge protocols for all NP relations. And this will be a building block that we use extensively in our work. So after this recall of zero-knowledge, let's go to equivocal commitments. So as James explained, we have a bit commitment scheme where a committer and the receiver, they might share some public parameters, and then the committer sends the commitment of a message M according to some randomness R. And we can assume that is in this vanilla commitment, the opening phase is just given by the committer sending M and the randomness R to commit it. Our protocol, in order to show equivocal commitment, is just replacing this randomness that the committer sends to the receiver by a zero knowledge proof that there exists some randomness R such that the commitment corresponds to the commitment of M under R. And from the properties of this vanilla commitment scheme, we can show that this protocol is binding and hiding. And moreover, we can show equivocality. And the equivocality is just showing that if instead of that the simulator against this malicious receiver can just use a zero knowledge simulator to convince that C is a commitment of a message M prime, where M prime is different from M in the first message. Okay, so this gives us the first step to have equivocal commitments. And as I said, using very close variants to the proof that James explained, we can have some sort of OT where now we have unbounded simulation. So I'll assume that we have this this type of OT for now. So now that you have unbounded simulator OT, I'll go up to extractable commitments by going via verifiable CDS. But okay, in order to do that, let me explain what this primitive is, what is conditional disclosure of secret. And again, here we want to do a CDS for some NP relation. So we want to have a verification algorithm such that it outputs 1 if and only if these inputs X and W belong to the relation. And the CDS for R is a protocol where we have two parties, the sender and the receiver. And the ideal functionality, so the goal of this protocol is to simulate this ideal functionality for CDS, where the sender chooses an input X and a message M. And the goal is that this ideal functionality should reveal M to R, if and only if R has an input W that belongs to the relation. So, in this ideal world, the sender sends them X and M to the ideal functionality, R sends W to the idea functionality, and then the idea functionality answers back to R, M if X and W belong to R, or perp otherwise. But unfortunately, we don't live in this ideal world, so we don't have access to this idea functionality, so we have to come up with a protocol that implements it. And in particular, we want protocols that have an extra property that we call verifiability. So let's assume that you have a protocol that you want to show that implements FCDS and is verifiable. So these protocols, they the sender and the receiver send messages back and forth. And in our case, we assume that these messages sent by the sender and the receiver, they might be classical or quantum. But in particular, we assume some classical messages, and we call tau the classical transcript of this protocol. We say that this protocol implements, this protocol is a verifiable CDS. First, if it implements this idea functionality, meaning that every attack to this protocol can be translated to the ideal world. But on top of that, we want that this protocol to bind X and M, meaning that even a malicious sender cannot change the message M that should be revealed to the receiver. And moreover, we want that this protocol binding to be verifiable. And actually, this is a crucial point that a crucial contribution of our result, showing how to do the verifiability, even if you have quantum messages here. Because in the classical world, it is simple to have this verifiability of CDS protocols, because for instance, the sender could just output the random coins used in the protocol, and this could be easily verified to check the transcript. But on the other hand, quantumly, the sender might have sent quantum states or measured quantum states received from the receiver, and in this case, there's nothing at the end that the sender could output in order to explain the transcript. So this is the subtle point that we need to verify, despite all of these quantum messages that have been sent back and forth. So more precisely, we want a protocol where, after interact with the receiver, the sender will output some proof pi, such that there exists a verification algorithm that accepts the transcript, the input X, the message M, and the proof pi. So it always accepts given the honest classical values of the protocol. And moreover, we want that no malicious sender could come up with a different pair of messages and proof, such that both this verification passes and the receiver does not get this message M tilde whenever she has the witness W. So we don't want that the verification is good for M tilde if R could not have gotten M tilde. Okay, and this is the verifiability property of CDS that is crucial in our extractable commitment. So before showing our protocol for verifiable CDS, I'll just show how it implies extractable commitments. And for that, I have to go through my extractable commitment protocol that is divided in 4 phases. In the first phase, we have a phase where the commitment and the receiver we allow the extractor to create a trapdoor. And in the second phase, we have a phase that would allow the receiver to learn the committed message if she has a trapdoor. Finally, we have the actual message commitment and the reveal phase. So these last 2 are the standard ones that we saw before. So let me give more details about each of these phases. So in the first case, in the first part, we just want the receiver to send a commitment of a value 0 according to some randomness R, and we're proving zero knowledge that C is indeed a commitment of a 0. Okay, this is that's a simple part. But then in this message extraction part, the committer and the receiver, they run a verifiable CDS protocol for the language of valid commitments of 1 and randomnesses. Okay, and in particular, the committer will choose as an input to this language the commitment that was sent by the receiver in the very first message. So notice that in the honest run of this protocol, this verifiable CDS will never will never give the message M, because C will always be no instance in the honest case. Okay. And finally, we have the message commitment, and it only it consists of the committer sending a vanilla commitment of the message, and on top of that, the committer proves in zero knowledge that the two messages are the same. So the idea is that you have a zero knowledge, that you prove that the commitment and the verifiable CDS are consistent, and this is the important part where you need verifiability of CDS. Finally, in the review phase, as before, the committer just sends the message and a zero knowledge proof that it corresponds to the commitment of that message. So to the committed value that was sent before. So from this protocol, we can show first that it is binding, and this is just because of the binding property of the vanilla commitment scheme. It is hiding, and the hiding property comes from the soundness of the zero knowledge, the security of the verifiable CDS, and the hiding property of the commitment scheme. And the very interesting part is extractability. So we have now to come up with an extractor that allows us to retrieve the message from the committer before the review phase. And we come up with this extractor by doing some hybrids. So in the first hybrid, we replace the zero knowledge proof by the simulator. So the idea is that since the extractor can rewind and it has some extra power than the receiver, we can replace it by the simulation, and the committer cannot distinguish the two by the zero knowledge property. In the second hybrid, we can the extractor can replace the first commitment. Instead of being a commitment of 0, it will be a commitment of 1. And it holds that because of the hiding property, this commitment is never open. The committer cannot check the difference of these two cases, and in this case, we have set up a trapdoor. Once you have a trapdoor, then the honest run of the verifiable CDS will reveal the message M to the extractor, and that's our goal, right? So this VCDS will give the message in the clear to the extractor. And that's why you can go from unbounded simulator VCDS to the extractable commits with polynomial-time extractors, because now when you consider VCDS, we're just considering the honest run of this protocol. And this gives us extractability. So finally, equivocality comes from, notice that the reveal phase is the same as the first protocol that I mentioned for equivocal commitments. So the equivocator is the same as I said before. So now that I showed how to go from unbounded simulator VCDS to extractable commitments, the only missing part is how to implement such a primitive. And as I said, this is implemented by using a tool called garbled circuits. And a garbled circuit protocol, it composes from 3 algorithms: the garbler, the encryptor, and the evaluator. And the input to the garbler is just the description of a circuit, of a classical circuit, from n-bit inputs to k-bit output. And the output of this garbler are then the garbler outputs this pair, that's the garbled version of the circuit, and a set of labels for each input bit. So for each input bit, this garbler will output two labels, one corresponding to the input 0 and another corresponding to the input 1. Then the encryptor receives as input these labels and some input x that want to compute C of x. And the encryptor just outputs the garbled version of this input, that is just the labels the set of labels corresponding to the input x, like to the bits of x. And the evaluator just receives the garbled versions of C and x and output y. And the properties that you want from these three algorithms, that first y is actually C of x. So just from the garbled version of C and garbled version of x, we can compute C of x. And secondly, that we have a polynomial-time algorithm called that's the garble simulator. And this garble simulator can output pairs of C and x that are indistinguishable from the original ones, only from given only C of x. So in other words, the pair of garble circuit and input, it can be generated only from the output of C of x. And Yao showed in '86 that actually from post-quantum 1A functions, we can construct quantum secure garble schemes. So let me quickly go through our protocol for verifiable CDS. So the main idea is that the sender can just send the input X to the receiver. And we can consider the circuit that outputs M whenever this circuit receives an input W, such that X and W belongs to the relation. And then the sender could just send the garble circuit and set as input to the OT the labels from the garbler. But here we have an issue that the sender could be malicious and send values that are not correct, and these would prevent us from the verifiability. So in order to prevent this, we have that the sender creates two lambda versions of these garble circuits and send them along to the receiver with the commitments of the message M and the commitments of the labels, on top of proving zero knowledge that these commitments and the garble circuits are correct, are consistent. Finally, the sender and the sender and receiver, they run these OT protocols, where now the messages are the pairs of labels and the randomness used to commit them. And the idea is that here we can use some of these garble circuits to test these labels and the commitments, and some of them will be used to actually extract the message M. So to do that, the receiver just pick a set of these garble circuits, and for some of them, so for the ones that belong to the set, the receiver will actually input the witness that she wants to retrieve the message. But for the ones that are not for the ones that are not in the set, she just picks a random string and use them to check if the commitment schemes are correct. So after having retrieved all these values from the OT, this receiver aborts if first the zero knowledge fails, or if any commitment is not correct or from this testing set, or if there is some I, or if she's not able to compute the evaluator. So we can show that, okay, yeah, I think I'm a bit run out of time. So we're able to show that this protocol is a CDS, and we show that it's also verifiable because the sender can just output this value R star that proves that the commitment is correct. And then we can show correctness and binding properties of this verifiable CDS. So with this, I complete all of this tree. And I'd like just to mention that our protocol has some also different properties. For instance, our protocol has polynomially many rounds because of the zero knowledge protocols. But if on top of that, we have a CRS, that's an extra resource that can be given to the parties, then we can actually achieve the OT in constant number of rounds. And in particular, with UC security, that's a much stronger type of security than standalone. And to conclude, I just like to say, okay, the main takeaway of these results that you can do secure multi-party computation in MiniQCrypt. And I think the main open question is, what else can you do? So for instance, can you do public key encryption or something else? And thank you for attention.
Okay, great. Thank you very much, Alex, for this nice explanation and the construction of your work. So I have a very short question. So could you maybe elaborate a bit on the connection of what you do with other constructions of OTs based on, for example, relativistic settings, or does your construction provide exactly the same outcomes? Or
no, I don't think so, because I think in relativistic setting, you have some extra properties that allow you to somehow to ensure that some parties don't learn everything. And I think that here, yeah.
I mean, not only relativistic, but also all these bounded. So if you would have a bounded storage or whatever, and
no, then with bounded storage, then you can do BBCS, for instance, directly, because then you can assume that they could not have kept all qubits without measuring. So in the bounded storage model, then you can use BBCS. You don't have to go through all the way long with all of these constructions. Then you have more direct approach.
Okay, perfect. So one question from Eddie Schutte is, how does extractability and equivocality imply that it is secure? I would think that it shows the opposite. If there is an equivocal protocol, isn't that a bad thing?
So yeah, that's something that always confuses me. But the point is, we don't, the equivocator and the extractor, they have extra power than the receiver and the committer. So in particular, we assume that, okay, we also use the fact that the extractor, for instance, can run the committer back and forth. So it can run run the committer, rewind it, and run it again. And the honest receiver could not do that. So this equivocator and this extractor, they cannot be used in practice. So it's just some abstract thing to show that in practice you could have extracted it if you had this power to go back and forth, but it's not a real thing, a real algorithm that you're running.
Okay, and then a question by Leo Colison is, why do you need both zero knowledge and cut and choose methods? For example, basically to open some circuits in this verifiable CDS construction. Isn't this zero knowledge enough to check consistency of the circuits?
So yeah, good question. So the point is, the cut and choose is used to check the inputs to the OT. So the point is, the zero knowledge only tells about the witness and about the garbled circuits and the commitment of the message. But the sender later could have chosen to send a different label, and then the receiver could not have noticed that.
Okay, great. Thank you. There's also other questions here, and it's very interesting discussions getting out of them. But I think that's, we can basically go to the roundtables, and then there's going to be the opportunity to ask directly the presenters of all talks, not only this last one. So I really urge you to press the button underneath and go to the roundtables. So thanks a lot to Alex and James and to all the talkers of this session, and have a nice afternoon.